Today, we're going to see a little more about how integration and differentiation interacts with the Laplace transform, and then we will be looking at Laplace transforms of systems of equations. Let's look at our most important formula, and that is that the Laplace transform of f prime of t in t space is minus f of 0 plus s Laplace transform of f of t over in S space. So now let's see what this has to say about antidifferentiation. And the way we're going to do this is let's suppose that f of t is in fact an antiderivative. It is the integral from 0 to t of g of u du. So the point here is that f prime of t is g of t. And what's also obvious from this is that f of 0 is 0 because the integral from 0 to 0 is 0, which gives us f of 0. Okay, so plugging into our formula up here, remembering that g of t is f prime of t, Laplace transform of g of t is 0, which is f of 0, plus s times the Laplace transform of f of t. And as a result, the Laplace transform of f of t is the Laplace transform of g of t divided by s. Thus, f, which is the antiderivative of g, so the Laplace transform of f of t is the Laplace transform of the integral from 0 to t of g of u du, is g of s over s. Okay, so integration in t space becomes division by s in s space. So remember, differentiation in t space was multiplication by s. Integration in t space is division by s. Now this formula is sometimes useful for doing inverse transforms quickly. Okay, so this particular inverse transform, L inverse of 1 over s times s minus 3, is doable by partial fractions, but it's actually probably a little quicker to use what we just learned. 1 over s times s minus 3 can be written as 1 over s minus 3 divided by s. And remember, division by s in s space is really going to be the same as integration in t space. So since 1 over s minus 3 goes back to e to the 3t, 1 over s minus 3 divided by s is going to go back to the integral of e to the 3u du between 0 and t. And that's actually pretty easy to do. That's 1 over 3 e to the 3u between 0 and t, which is 1 over 3 e to the 3t minus 1/3, which is what you get at the bottom limit. Okay, now probably more interesting is what happens when we take the derivative of a transform. So cap f of s is the Laplace transform of little f of t, which is the integral from 0 to infinity, little f of t e to the minus st dt. F prime, realizing here this is differentiation in s, is going to be just dds of that integral. And for well-behaved integrals, and this is 1, you can just move this derivative inside the integral. And when you take that derivative, f of t is a constant, e to the minus st becomes e to the minus st times the derivative of minus st, which is minus t. Remembering here we're differentiating with respect to s, so we end up with minus t e to the minus st dt. We slide that minus t over here, and it sits with the f, and now this thing is just the Laplace transform of minus t f of t. So the derivative of cap f is the Laplace transform of minus t times f of t. And using linearity, we can write this as the Laplace transform of t f of t is minus the derivative of cap f of s. Now, this turns out to be useful to derive a variety of formulas, and probably the one that's most interesting to us are these resonance type formulas. T sine bt, which you may recall appeared when we solved problems where we were driving oscillators at resonant frequencies. So the Laplace transform of sine bt is b over s squared plus b squared. The Laplace transform of t times sine bt is, according to what we just discovered, going to be minus the derivative of this thing with respect to s. And we just rewrite that now as s squared plus b squared to the minus 1. Use our standard chain rule for differentiation. We get b minus 1 s squared plus b squared to the minus 2 times 2s, which when we do all the algebra becomes 2 times b times s over s squared plus b squared squared. Now, again, because of linearity, this transforms to that. So 1 over 2b of this transforms to s over s squared plus b squared squared. And we can see how useful this is when we look at the following differential equation. X double dot plus omega naught squared x equals cosine omega naught t. X of 0 equals x dot of 0 equals 0. We've seen this problem before. We solved it back in the day when we were doing method of undetermined coefficients. It was not a whole lot of fun. Here, when we take the Laplace transform of both sides, the Laplace transform of x double dot is minus x dot of 0 minus sx of 0 plus s squared cap x. The Laplace transform of omega naught squared x is omega naught squared cap x. And now cosine of omega naught t, we've seen, becomes s over s squared plus omega naught squared when we transform it. So these terms are gone because the initial conditions are 0. And we've just got s squared plus omega naught squared cap x is s over s squared plus omega naught squared. We divide through by s squared plus omega naught squared, and we've got s over s squared plus omega naught squared squared. And this is actually just the transform we've talked about. We just saw that the Laplace transform of 1 over 2b t sine bt is s over s squared plus b squared squared. And this is exactly what we've got with omega naught equaling b. So we can see that when we back transform, what we get is x of t is 1 over 2 omega naught t sine omega naught t. Now, this does get somewhat uglier when we have sine terms as our driving terms, but the principle is the same, and we can find the resonant terms in the same fashion. Laplace transforms can also be used to solve systems of differential equations. And let's look at a system that we've solved now by a couple of other means. X dot equals 2x minus 4y, y dot equals 2x minus 2y, x of 0 equals 8, y of 0 equals 2. And you'll recall we've solved this using differential operators, and we've solved it using matrix methods. Okay, so now we're going to transform. The basic idea here is that the Laplace transform of little x is going to be cap x, and the Laplace transform of little y is going to be cap y. So we Laplace transform the first equation. Laplace transform of x dot is Laplace transform of 2x minus 4y. Okay, x dot transforms exactly the way that we're used to, minus x of 0 plus s cap x. This becomes 2 cap x minus 4 cap y. And same idea for the y dot equation. And we get minus y of 0 plus s cap y equals 2 cap x minus 2 cap y. Okay, and x of 0 is 8, which goes here. Y of 0 is 2, which goes there. So we move all of the Laplace transforms onto the left-hand side, and the constants move to the right. And that this minus 8 here is an 8, this minus 2 here is a 2, and we've grouped the x's and the y's. Now, this should look sort of familiar. When we did this with differential operators, there was a d minus 2x plus 4y and a minus 2x plus d plus 2y. The difference here is that the initial conditions have come along. With the differential operators, it was 0 here. Okay, so we're going to solve essentially the same way. We want to kill off one of the terms. In this case, it's going to be the x term. So we're going to multiply this equation by 2 and this equation by s minus 2. And on the top, we just get 2s minus 2x plus 8y equals 16. Here we're multiplying through by s minus 2. So we're getting 2s minus 2x plus s minus 2 times s plus 2y equals 2s minus 2. And now when we add these things, the x's cancel, and we get this s minus 2 times s plus 2y plus 8 cap y equals the sum of these two. There's a 2s, a minus 4 plus 16, so that's a 2s plus 12. Okay, and now we're going to do some algebra and discover that that was s squared minus 4 cap y plus 8 cap y equals 2s plus 12. And add these two together, we get s squared plus 4 cap y equals 2s minus 12. Divide through by s squared plus 4. 2s plus 12 over s squared plus 4, which we split up as 2s over s squared plus 4 and 12 over s squared plus 4. S over s squared plus 4, we recall, goes back to a cosine. This is going to go back to a sine, but since b is 2 here, we need a 2, which means we factor a 6 out. So we're going to have a 2s over s squared plus 4 plus 6 times 2 over s squared plus 4, which is going to go back to 2 cosine 2t plus 6 sine 2t. And we're not done. We need x. And there are two options for calculating x. One of them is just looking at one of our equations that we got early on, minus 2x plus s plus 2y equals 2, and just solving that for cap x, which looks like this. Now we plug in what we got as the Laplace transform of y into here, do some algebra, and what we end up with finally is 8s plus 8 over s squared plus 4, which we can split up as 8 times s over s squared plus 4 times 2 over s squared plus 4, and we get 8 cosine 2t plus 4 sine 2t. Now our other option is to go back to the actual differential equation, y dot equals 2x minus 2y, and solve that for x. Since we have a closed form solution for y, we can just plug it in here. Y was 2 cosine 2t plus 6 sine 2t. Its derivative is thus minus 4 sine 2t plus 12 cosine 2t. You shove that in for y dot. Y is this. 2y is 4 cos 2t plus 12 sine 2t. Add them all up and divide by 2, and you get 8 cos 2t plus 4 sine 2t. Now it's worth remarking that this second method does not work very well if we have a system of 3 or more equations, because when you solve for one of them, you've still got 2 others floating around. And you're probably in that case going to have to inverse transform at least a couple of the variables before you can try something like this.